So section 3.3 asks us to solve trigonometric equations. We're going to buzz through a lot of these things here, so hang on to your hats. Now, in particular, if you have something like sine of theta equals 1/2, let's take a quick look at what the instructions might look like on an exam or in my math lab. So that one is down here. So solve each equation, give a general formula for all solutions, list 6 solutions. Okay, so what's going on? What do you mean general formula? Well, let's take a look at this in terms of its graph. Here's the graph of the sine function. If at the same time you look at the graph of y equals 1/2, you notice that there's a lot of places where these things intersect, right? There's an, I don't know, infinite amount of them. So let's see if we can't figure out where those are intersecting. So to do that, we can look at things a couple ways. First of all, if you have a good unit circle, you could just look at that and say, oh, okay, well, I want to know where one of the coordinates is 1/2. Now, if I'm looking at sine of theta equals 1/2, then which coordinate should I be paying attention to on my unit circle? Sine of theta is 1/2. Sine is which coordinate on the unit circle? The y coordinate, thank you. So really, it's going to be places like here and here. There's 2 of them, pi over 6 and 5 pi over 6. Now, if you're looking for just the solutions in the unit circle, that is in the range 0 to 2 pi, then that's good. Those are the only 2 you need right there, pi over 6 and 5 pi over 6. Anything beyond that is going to be outside of the range of 0 to 2 pi. But keep in mind the second part of this problem is to list a general solution and then list 6 specific solutions. So we got a little bit more work to do ahead of us. So let me chop this off for a second and let's look at just a couple solutions. Here and here, these don't feel like they're the same part of the sine wave, right? One of them's on the downside, one of them's on the upside. So, yeah. What I'd like to do is I'd like to start out with one solution and then characterize the next solution and the next one after that. So let's work on that. Sine of theta equals 1/2 has 2 solutions. Theta could equal pi over 6, or theta could equal 5 pi over 6. Those are our 2 solutions in terms of radians. But we know something about our angles. Our angles have a lot of different names for the same coterminal angle, and that is I can add multiples of 2 pi. So I can add n times 2 pi. That's n times 2 pi. And this gives you your general solution. Now you don't have to use both of them, you can use either of them. But these are general solutions. From there you can get your specific solutions. If you wanted specific solutions, hey, that's fine. Let's do that. Let's get a few specific solutions. These are our general solutions. General solutions. Our specific solutions can come from plugging in values of n here. So we'll start with the first one. N and theta. Now it might be helpful to play around with this a little bit and come up with a more user-friendly form for your theta. So let me come down here. That's going to be pi over 6 plus, I'm going to rewrite this as 2 times n times pi. And, well, it'd be helpful if I had a common denominator. Right now, you can think of this as being over 1. So if I wanted to get a common denominator, what I could do is multiply by 6 over 6. That'll give me 12n pi over 6. Or better yet, if I bring all this together over my common denominator of 6, I can write pi plus 12n pi, or if I factor out the pi, it's going to be 1 plus 12n times pi, all over 6. So a little bit of extra work there to get that nice, neat general form. But once you've got that general form, then the rest of this should be pretty easy. Let's put in a few values for n just to see what the general solutions look like. And then we'll go back and look at Desmos and make sure that it actually lines up the way that we think it does. So, all right, let's put in values like 0, 1, 2, and 3. We can also put in -1 and -2 as well, just to get in a couple negative solutions. We'll start with 0, and we'll put that in here. So let's see, it's going to be 1 plus 12n pi over 6. If I put in n equals 0, then I'll just get pi over 6. All right, that's the basic solution that we kind of expected anyways. What about if I put in n equals 1? What do I have up here in the numerator? 13, perfect, 13 pi over 6. And then you put in a 2, and you get 25 pi over 6. And see, once you've got this nice formula, you can get as many of these as you want. How about -1? What if I put in -1 up here? What would I get then?
-11.
-11 pi over 6. Thank you. I think Michael got that one first. Thank you. So let's just kind of look back and see that this matches what we expected. So I'll shut this off, turn this one back on, and take a look here. 5 pi over 6, okay, that's looking good. Let's see, no, I'm turning on the wrong ones, my bad. Pi over 6, and then 13 pi over 6, and 25 pi over 6. Notice I'm turning on the same point in each wave. So if I go backwards a little bit, then I want to turn on this point. There's my -11 pi over 6, and according to the formula, I can go back and find this one, that'd be -23 pi over 6, etc. You can get as many of these specific solutions as you want. All right? Now, up to you. You want me to play that same game with this one over here? Get a common denominator, go through all that stuff again, or are you comfortable doing this stuff for yourself? Is that a good? I'm good. James, want to do it again? Okay, let's do it then. Thank you. All right. So over to here, I'll do another little table, n and theta. This time I've got to play around with 5 pi over 6 plus 2n pi. And I'm going to do the same thing here that I did just a moment ago. Now, I want a common denominator for both of these. Right now, it's not written, but it's understood that the denominator here is 1. So to get a common denominator, I'm going to multiply by 6 over 6. Because multiplying by 6 over 6 is like multiplying by 1. It's not going to change the value of the expression, but it'll help me rewrite it in an equivalent way. So that's going to be 5 pi over 6 plus 12 pi over 6 times n. Forgot the n there. Now, these have a common denominator, so I'll put that over a common denominator. And I'm going to factor out the pi from this. So it's going to leave behind 5 plus 12n times pi. And that's a nice general expression for theta. So with that expression, and I don't have room to squeeze it in there, you can do the same thing here. -2, -1, 0, 1, 2, and 3. And write down 6 different particular solutions of this equation. Now, if n is 0, we get 5 pi over 6. How about if n equals 1? What will we get then?
17.
17 pi over 6.
Yeah, perfect. 17 pi over 6, and then 29 pi over 6, etc. And you can get as many as you want from here. So the idea is to come up with a general solution. I kind of regret that they asked for 6 particular ones. I think 3 or 4 would be good enough, but you know, that's the way they stated the problem. Let's look here and see that that actually works. So we're going to deal with the other part of the wave right here. Let's see, let me go over to the positive side of things. So 5 pi over 6, 17 pi over 6, 29 pi over 6, etc. So it matches. Now that's a lot harder to do with the graphing calculator, but at least you can see it, and hopefully it's convincing. Are we good with that one? Good with that one's kind of like a nice little warm up here for us. Precious. Okay, thank you. All right, let's keep going. Now, one thing that should be familiar to you from our work in the first few sections is that the sine function is periodic. In fact, how long does it take before the sine function repeats itself? 2 pi, right? Same thing for the cosine function. The cosine function repeats itself every 2 pi. But is that true about the tangent function? Let's take a look here. Here's a tangent at 0, and then here's that same point in the graph a little bit later on. What's the period of the tangent function? Pi, yeah. Tangent and cotangent have a period of pi, so they repeat themselves a lot more frequently. Now that's going to have implications for when we solve things. One thing that I would be familiar with, I'd suggest you be familiar with, is, and let me see if I can find it here for us. Yeah, let me change the view here. This part right here. Remember what these circles are out here on our unit circle? What's this the value of? That's the value of tangent. So tangent and cotangent are going to be 1 or -1 at these multiples of pi over 4. So pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So it's helpful to just have that down, keep it memorized. Let's see what it matters for us here when we start looking at the next problem. We're going to find the tangent of theta equal to 1. So I'll call this example B. Tangent of theta equals 1. Well, I know where the first one occurs. All right? Theta equals pi over 4. We know that. But unlike our values for sine and cosine, tangent repeats itself every pi unit. So it'd be plus n pi. Now I'll do a little repeat here for us on some of this stuff. Pi over 4 plus n pi over 1. If I wanted to get common denominators here, what do I need to multiply that by?
Both by 4.
Yeah, 4 by 4. So that's going to give me pi over 4 plus 4n pi over 4. And that all factors out pretty nicely. It's going to be 1 plus 4n times pi all over 4. And again, you can get your general solution. This is your general solution. That's it. I don't need 2 cases like I do for the graph of the sine or cosine. This is my general solution. You don't have to put it together all factored like this. My math lab should take it like this. You know, I like it here better because it makes it a little bit easier in this next part. Plugging in n equal -2, -1, 0, 1, 2, and 3 for our values for theta. At n equal 1, you're at pi over 4. How about n equal 2? Or n equal 1?
5 pi over 4.
5 pi over 4, and then 9 pi over 4, 13 pi over 4, and so on. I hope you see all I'm doing is I'm substituting different values for n here. So that'd be negative 3 pi over 4 and negative 7 pi over 4. Awesome. There you go. These are your particular solutions. Lucas?
Using the algebra, please.
Yes.
Why did you multiply down on the 4 to n pi over 1?
I wanted a common denominator. Right now, the denominator here is understood to be 1. So by multiplying by 4 over 4, that gave me a denominator of that second fraction of 4, so that I could add those together. Cool. Thank you. Let's spice it up a little bit. Let's take a look at some different examples. Keep track of my scrap paper here. And I'll show you what this one looks like in your assignment in my math lab first. So we'll do problem number 49 here. It says you want to find the sine of theta equal to 0.4. Yeah, I should wouldn't have. Sine of theta equals to 0.4. Okay. All right. So we have to think about what's going on with that one. Now you can get kind of a Desmos or calculator solution to this kind of stuff. It's okay. So here's y equals sine of x, and then y equals 0.4. You're not going to get any nice friendly values like we did with some of the other ones. That's okay. Now they are restricting us in this first problem here to values of x between 0 and 2 pi. So of all the values we have to consider, we really only need to look in this interval 0 to 2 pi. How many solutions do you think we're going to get? 1, 2. Now we get a lot more if we were looking beyond the interval 0 to 2 pi. That's okay. They just said look to 0 to 2 pi. All right. We'll do exactly what they said. Let's keep going. So, where'd my unit circle go? Here. So let's look at the unit circle. And in particular, what I'm going to do is I'm going to come down to this one and just draw myself a line at about 0.4. All right. So I've got y equals 0.4. And I'm going to solve sine of theta equals 0.4. I need these two solutions. There's two places here. Unfortunately, our calculator and or Desmos is only going to give us one of these in a direct fashion. If I've got sine of theta equals 0.4, here's what I can do. Let's see. Sine of theta equals 0.4. Now I'm leaving myself a lot of room here, generous amount of room, because what I'm going to do is I'm going to undo the sine on the left-hand side. Now by undo, what I mean is apply the inverse function, the opposite of the function. So what's the inverse or opposite of the sine? Somebody said arcsine. Cosecant is the reciprocal. If I want the inverse, I'll just do sine inverse on both sides. Now look at the magic that happens on the left-hand side. Sine inverse of the sine of theta, those collapse. I just get theta equals the sine inverse of 0.4. Now, that's going to give me an angle where? You guys just took a test on this. what's the range for the inverse sine? Adam, got that one? What's the range for the inverse side?
Negative pi squared and to pi squared.
Negative pi over 2 to pi over 2, yeah. Yeah, thank you. That's all right, it's all right. I mean, after a test, I think my mind would be a little bit mushy too, so, yeah, there you go. Thank you. So, you're gonna get an angle in here. All right, let's get that out for a graphing calculator. So, let's see here. Ooh, got a lot of extra stuff here. Let me get rid of that. What mode should we be in? Well, take a look at the problem. It says we want answers in the interval 0 to 2 pi. That's kind of telling you, right? What mode should I be in?
Radians.
Radians. All right, so I'm in radians. I'll do the inverse sine of 0.4, and I get 0.411. Okay, that's fine, 0.411. So 0.411, that's this angle. But I know that there's another solution over there. I've got to find it. Let me give you a little clue though. We know a little something about that angle. Now what we want is we want to find the angle starting here and ending up here. Well, I know an angle that's kind of close to it. If I started here and went all the way to the x-axis, what angle would that be? 180. What would it be in radians? It'd be pi, right? All right, thank you. So it'd be pi all the way here, but I need to back up just a little bit. I'm a little bit short of pi. So what would I write here to get that second angle? Pi minus 0.411. That's my other angle. And you just get it by looking at the unit circle and doing a little figuring. But that's it. In fact, we can check it and prove it to ourselves that it actually works. So, give you a second to copy that down, and I'm going to pull out my graphing calculator again. Here's kind of a cool trick. First of all, I'm going to type in pi, so second and then pi, minus, I don't know, does anyone want to type this in for me? Nah, never mind. I'll do it this way. If you hit the second key, then the opposite key, it types in your previous answer. Ooh, that's cool. Now I press enter and I get 2.73. Okay. 2.73. Now I can check that pretty easily. How can I check that? Well, I should be able to take the sine of that, sine of my previous answer, so there's that fancy little keyword again, and what should I get?
0.4.
0.4. Bingo, nailed it. Wow. So you can prove to yourself you got this right before you even hand in a test. So those are your two answers. Now, if need be, you can generalize from there. You can add, multiples of 2 pi to this, multiples of 2 pi to this, and get as many. I'm sorry, I need to be on the screen here. Multiples of 2 pi to this, multiples of 2 pi to this, and you can get as many answers as you want. But they only wanted answers from 0 to 2 pi, so hey, we're good. We're all set there. Okay. Let's do another one like that. Questions on this one before I move on? Okay. Let's take a look at kind of the next one over. Cosine of theta is 0.6. Gonna be a little bit of a twist in this one. So we're gonna use this one over here. Cosine of theta is 0.6. Now the twist in this one is that cosine is not dealing with the y coordinate. What does cosine deal with, Amani? The x coordinate, thank you. So I want to look at where the x coordinate is 0.6. So, okay, so that's gonna be here someplace. So here and here. Okay. How am I gonna solve here? What do I have to do to get theta by itself? Give you a hint, it's very similar to what we did just a minute ago. Yeah, excellent, thank you. Do the inverse on both sides. So here and here, here and here. So cosine inverse, cosine inverse. Crystal, on the left-hand side, what simplification do I get?
Simplification, it just becomes theta.
Yeah, that's exactly what I was looking for. Thank you. Awesome. She's like, ooh, big sigh of relief. I got it. Awesome. Let's keep going. On the right-hand side, well, we need the inverse cosine of 0.6. But notice something. There's going to be two solutions. There's two places on the unit circle that have a cosine of 0.6. Sean, help me remember. What's the range of the inverse cosine? Ooh, it's like,
I would have done better on the test if I knew that.
All right, some help? Anyone?
0 to pi.
0 to pi. All right, so cosine inverse is going to give me one of my angles. It's going to give me this one here. I'm still going to need to figure out that one down there. So, okay. Let's see what we get here. And thanks for being a good sport, Sean. All right. So that one here, and I'm going to need this one here. So let's do the inverse cosine of 0.6 and see what we get. So let's clear these out. Inverse cosine, 0.6. Okay, 0.927, etc. That's going to be my angle up here. 0.927. 0.927. But I need to get this other angle over here. Now this other angle over here is close to an angle that I do know. Does anyone know what angle I'm referring to? What angle do I know that goes all the way around here? In radians. Yeah.
2 pi.
In radians, 2 pi, excellent. So I either get theta is 0.927 or 2 pi minus 0.927. So that would be my other answer. And since we only have to worry about solving in the range of 0 to 2 pi, that's it. We're done.
What is the 2.73 next to the sine?
Oh, this is like a decimal approximation of, the first few digits of this. This is actually an infinitely long number. So I should maybe put ... meaning it goes on forever. Same with this. This is just the first few digits. ... Yeah, so it's just really reflecting that it's the decimal approximation of this. Okay? Yes? I think for the homework, you're probably going to end up putting in the decimal. So what you could do for that would be type in 2 and then pi minus your previous answer. So for me, the easiest thing to do is hit the second key, then the opposite key, and there you go. Now you can round that to whatever you need. Okay. The only other thing that I could see that they would ask you to put in, and I just don't envision it happening, would be the cosine inverse of 0.6 or 2 pi minus the cosine inverse of 0.6. I just don't see them doing that though. Okay. All right, appreciate the question. Thank you. Let's keep going. We're gonna still solve things in the interval 0 to 2 pi. Question?
I'm just tired.
Oh, okay. And next I want to go to it's problem 37 in your homework. Let me pull that up for us here on the screen. So it's coming back, I said 37, it's 27 right here. Oops. Why is that doing that? All right, right here. Sine of 3 theta equals -1. Lot going on here. Let's take a look at it. Sine of 3 theta equals -1. So, I don't know. Not sure. Is this example D by now? Not sure. Well, we're going to solve this in the interval 0 to 2 pi like we did before. And I want to get theta by itself. So what's been working for us so far in trying to get theta by itself? What have we been doing? Taking the inverse. Good. So let's do the inverse of this. So the inverse sine. And on the left-hand side, things cancel. Peter, what's left on the left-hand side when I finish canceling?
Theta.
Close.
3 theta, sorry.
3 theta. 3 theta, thank you. Now, let's think about the inverse sine of -1. That's going to be the point on the unit circle where sine is equal to -1. What's the value of that in radians? Sergio, what would that be in radians? Where does sine of theta equal -1? So sine is the y coordinate. Sine of theta would equal 1 up here. Looking for -1.
3 pi over 2.
All right, some help there, 3 pi over 2. You agree with that? Okay, cool. So that's going to be 3 pi over 2. But it could also be 3 pi over 2 plus 2 pi again, plus 2 pi again, plus 2 pi again. Basically multiples of 2 pi. So let me just build that into my formula, 2n times pi. So that's everything. Okay. Now, I need to solve for theta here. That's not going to be too hard. But let me suggest a way to do it. Rather than just divide by 3, I'm going to suggest something a little different. Instead of dividing by 3, how about if you make your life easier by multiplying by the reciprocal? So what I'll do is I'll multiply everything by 1/3. So 1/3, 1/3, 1/3. Okay. This equation is going to simplify. I'll end up with theta equals, well, the 3's cancel, right? Pi over 2. And here I get 2 pi n over 3. Okay. What would a common denominator be this time?
6.
6 is a common denominator. So what I'll do is I'll get a common denominator for both of these. All right. Let's see. Allie, what should I multiply this by to help get a common denominator?
3 over 3.
All right, 3 over 3, and then over here by 2 over 2. Excellent. So that gives me 3 pi over 6 plus 4 pi times n over 6. And great. These have common denominators. So let's bring that together over 6. And I'll factor out the pi. It's going to be 3 plus 4n times pi. Beautiful. Now, why am I doing all this? Well, remember they asked us for a solution in the range of 0 to 2 pi. 0 to 2 pi. And I can't just stop with the first one that I see. I've got to make sure that I've got all of them. So let's make ourselves a little table here and keep on putting in values of n until we get past 2 pi. So I'll start with n equals 0. If n equals 0, that's 0. I get 3 over 6, which is 1/2. So I get pi over 2. Okay, that fits in my interval. How about n equal 1? What does that put me in terms of theta?
7 pi over 6.
7 pi over 6, all right? Is that less than 2 pi?
Yes.
Yep, still good. Let's try n equal 2. So that's going to be 8 plus 3 is 11. No, wait. Yeah, 11 pi over 6. Ooh. So if we try one more, if we go to 3, then we get 15 pi over 6. At which point that's too big. Because 15 over 6, that's more than 2. So it's too big. So your 3 solutions that you get are these right there. Those are your 3 solutions. Now you have to do this extra little bit here because you didn't have just sine of theta, you had sine of 3 theta or some multiple thereof. So that's why we had to do all this extra little bit here. Yes, sir.
Can you zoom out? Can you scroll up to the top?
Yep. Comments or thoughts, other questions on example D here? Let's keep going. Let's try problem number 44. So 44, again, let me show you what that looks like in what would be the textbook if you had a printed copy of it. I said 44, I lied. Which one do I want? I want 50. No, yeah, let's see. Oh, 62, my bad. So 62 here. 2 cosine squared theta plus cosine of theta minus 1 equals 0. So this one right here, let me copy that down. 2 cosine squared of theta plus cosine of theta minus 1 equals 0. Now some of you could probably get away without necessarily doing the factoring trick that I'm going to do, but some of you might not. If you take a look at this, this is a quadratic equation. It just happens that it's a quadratic equation with the variable cosine of theta. Let's make kind of a quick substitution to dial it down a little bit. Look a little like confusing. So we're going to substitute u equal to cosine of theta. And what's that going to give for us? Well, it's going to change this equation into 2u squared plus u minus 1 equals 0. This is just a temporary little trick so that we can concentrate and figure out how this is going to factor. Now, factorizations of this sort aren't people's forte, usually speaking. But this one's not too bad because it's going to factor into two binomials, the first of which has to have a 2u and the u. Right? The first two numbers have to multiply to this one. The last two numbers have to multiply to -1. Well, fortunately, there's not too many choices of things that multiply to 1. It's just 1 and -1. The question you got to figure out is which one of these is positive and which one of them is negative. You can do it by trial and error. That's fine. You plug in a plus here and a minus here, and if that works, great. If it doesn't, try it the other way. And I'll tell you it's the other way. It looks like this. Now I'm hoping that you don't have to pull out the quadratic formula for this, but you could. I mean, there's nothing wrong with that. I'd rather see you get it right doing the quadratic formula than just staring at it blankly. But if you've got it factored, then I'm hoping that you can tell me what the solutions are here. When does u plus 1 equal 0?
When you use -1.
When u is -1. And 2u minus 1 equals 0. Well, that's going to be when u equals 1/2. So I've got these two possibilities. Except one thing. Remember, this is a trig class. We're not solving algebra problems here. So we got to go back and say, oh, well, this was really taking the place of cosine of theta. So I've got cosine of theta equals 1/2, or cosine of theta equals -1. Those are my two possibilities. Now, do a little Gedankengang experiment here, a little thought experiment. Cosine is the x-coordinate. Where does the x-coordinate equal -1? Try and do it without looking at your unit circle.
180.
180 at pi, right? So that's one possibility, theta equals pi. Now I can't go 3 pi, I can't go -pi, because I'm trying to solve this in the interval 0 to 2 pi. So that's one solution. That's the only solution I get for this part of it. But here, there's two places where the cosine of theta equals 1/2. You're looking for the x-coordinate equal to 1/2. And again, if you want to look at your unit circles, that's fine. X-coordinate of 1/2 is pi over 3 and 5 pi over 3. Pi over 3 and 5 pi over 3. And that's it. Done. Nailed that one. Nice.
So the answer would be all three.
All three of these, yep. Yep. Okay. How are my homies doing? I'm talking to the people online, not you guys here. All right. Feel okay? Thumbs up? Leif? Yes? All right. All right, let's keep going. Let's try another one like that, and then I'll finish up with doing one numerically with your graphing calculator. So let's see here. So we'll call this one example F. Two sine squared theta minus 5 sine of theta plus 3 equals 0. Suggestions. Where would you start? Again, we're trying to solve this in the interval 0 to 2 pi. Yeah, substitute. Thank you. So what are we going to substitute this time? Colleen, what do you think we should let u equal? suggestions? U would equal sine of theta. Thank you. So that turns us into 2u squared minus 5u plus 3 equals 0. If you're not good at factoring, you can use the quadratic formula. I'll give you your choice. You want me to factor it, or do you want me to use the quadratic formula? Either way, what's going to happen is you're going to get down to the point where you have some solutions for u. You'll have a u equals something and u equals something else, and then you substitute in your sign and finish solving. Now, if you can get there by factoring, all the better. But if you can't factor these things, and I'll be honest, when I was in your chair, I sucked at factoring these things. I was awful. I would always use the quadratic formula to solve these. I mean, if there wasn't a 2 in front of it, yeah, I'm good. When you put that number in front of it, it was awful. So your choice, quadratic formula or no?
Factor.
Factor it, all right. All right, quadratic formula, just a reminder, x equals negative b plus or minus the square root of b squared minus 4ac over 2a, sung to your favorite college fight song. I've also heard it sung to Pop Goes the Weasel, but I'm not gonna, accost you with my singing here. All right. So this one I have to be a little more thoughtful about than the last one. I know I start out with a 2u and a u, and let's think about that from there. Both of these have to be minus. Minus and a minus. Why? Because you got a negative here, but you got a positive here. So you have to have minus times a minus would be a positive, but when you add things in the middle, you're going to get a negative. So, okay. Now, there's not too many things that multiply to 3. There's 1 and 3 or 3 and 1. It makes a difference as to which order you put it in. So where do I want to put it in? If I put in a 1 here and a 3 here, when you multiplied these outside two, I'd end up with minus 6u, and then minus u again, that'd be a total of minus 7u. So that's not going to work. So what we'll have to do is put it in this way. 2u minus 3 and u minus 1. What's that?
How'd you get the u minus 1?
I knew that the only two numbers that are going to work here are 3 and 1, and it was just a matter of choosing which order.
How did you know that though?
Well, because 3 is a prime number. The only numbers that multiply to 3 are 1 and 3. So I got lucky there.
Oh, that makes sense.
All right. Now, this times this equals 0. One of these things has to be 0. So either 2u minus 3 equals 0, which means u equals 3 halves, or u equals 1. Okay. Let's go back now and recall that u was taking the place of sine of theta. So sine of theta equals 3 halves. Sine of theta equals 1. Let's see if we can't solve this one without necessarily resorting to a graph or a graphing calculator. Where does the sine function, where's the y coordinate equal 1? What point? And in radians?
Pi over 2.
Thank you. Pi over 2. So theta is pi over 2. And that's the only place that we got to deal with. Now, if you're looking at this going, I don't know, I can understand that. So you can try taking the inverse sine on both sides. So there, inverse sine, theta. And when you take the inverse sine of 3 halves on your calculator, it probably says domain error. Why is it doing that to me? Exactly. 3 halves is too big, right? If you're looking for a y coordinate of 3 halves, well, the biggest y coordinate you've got is 1. 3 halves would be up here. There's no angle on the unit circle with that as a y coordinate, so there's no solution. please don't write domain error. I'm not really a big fan of that. And if my favorite teams are losing, you might lose a point there. So there's really only one solution here, and that's theta is pi over 2. Awesome. I got an answer. Go ahead. No, because it's not even an extraneous solution. It's a good question. This is just not a possibility. In fact, if you were to graph this, and I'm sorry I don't really have the time to graph it, but if you were to graph this, say y equals this, and look for where it crosses the x-axis, you'd only see it, at pi over 2, at least in the interval 0 to 2 pi. Okay? Thank you. All right, last one. This one, take out your graphing calculators for. We're going to try and solve where x squared equals x plus 3 cosine of 2x. We're going to try and solve that graphically. Now, here's the way we're going to do this. We're going to plug in two functions. We're going to plug in y equals x squared on the left-hand side of this, and y equals x plus 3 cosine of 2x on the right-hand side. So you're going to plug in two different graphs, one for the left-hand side, one for the right-hand side. And then the idea is to look for where the graphs cross each other. So let's go to the graphing calculator. Let me clear out a bunch of stuff. And I think I've already entered those functions in. Yeah. Now, this is kind of a cool trick if you ever needed it. If you want to have functions in here, but you're done using them for the moment, might want to go back to them later, you can deselect the equal sign, and then it won't graph it, and you won't get a table for it. But if you want it to graph, then you come over here and you press the Enter key, and notice that darkens the equal sign, and now it's going to graph. If I do likewise here, you can get both of them to graph. So there's my two functions. I want to make sure my calculator's in radians. I'm going to solve this in radians. And if you're looking at that going, I have no idea where this is going to intersect. I have no idea what to set up the window as. That's okay. Here's a trick, nice little thing you can do. If you're unsure of where to start your window, we're going to go with the standard window, which is -10 to 10 on the x-axis and -10 to 10 on the y-axis. The easy way to get there is to hit the zoom key and then zoom 6. That's zoom standard. That gives you a standard window. Generally speaking, from there, you can figure out where you want to go to kind of zoom in on things after that. So you should have a graph that looks something like this. Has everyone got that? Okay. Now, let me show you another cool trick. If I want to focus my attention on this area right here, I could sit there and twiddle my thumbs and think about, well, gee, what should the window be? But how about if we make it a little bit easier? Hit the zoom key again. This time, select the first option, zoom box. So zoom, and then enter. And that puts a little cursor on the origin. Let's move it around, move it a little bit to the left of the origin. Maybe somewhere over here. It doesn't have to be exactly where I'm looking. I'm going to go a little bit below the x-axis too. And when you get to someplace in the third quadrant, a little bit lower than the x-axis, press the Enter key once. And then move up. And if you scroll up a little bit, and then scroll to the right, this is going to be your new viewing window. So I want a nice little box around the area that I'm interested in. So when you get that second corner adjusted the way you want it, then press the Enter key again. So, bam. There you go. And now it's zoomed into the interesting part of the graph that you selected. So did that work on your graphs? Yes? All right. Now, I need to find this point of intersection. In fact, I'll find both of them just to give you the extra practice. So, to get that point of intersection, hit the second key, then the calc key. So the second key and the trace key, really, I guess, has calculate above it. So that's what we're gonna hit. Does there look like there's something, an interesting option on this menu? Yeah, 5, intersect. Says it pretty clearly. Now, it's kind of funny the way this works. You're gonna end up pressing enter a total of 3 times. So move your cursor somewhat close to the point of intersection that you're interested in. So use the arrows to move that over there. And when you get somewhat close, and it doesn't have to be terribly close, you're gonna press enter a total of 3 times. 1 for the first curve, 1 for the second curve, and 1 more again.
Mine just made a version of it. After I press.
You press after you click on the bottom.
I'll repeat that again. Lucas, bring me your calculator.
Sorry.
All right. So, let's go through those steps once again.
I already got
So-
the box in there.
You gotta press enter again so that it zooms in.
So for every time I
Okay.
press enter, errored.
Okay. All right, so to repeat this again, you're gonna hit the second key, then the trace key. Select number 5. And cursor to close to where you wanna go. That's close enough. You don't have to be terribly close. You press enter to give it a guess from your first curve, enter again from your second curve, and enter again for reasons which I can't explain. And there you go. So your x coordinate there for that second intersection is 0.8109, et cetera, and you got more digits there than you want. So, in fact, if you wanted even more digits, if you left this graph and just typed in x, it now has the value that you just found. So you got as many digits there as you could possibly want. Okay. Looking good on that second one? Can you find that point of intersection? You would be asked to round it to so many digits. Yeah. All right. Excellent. Let's stop things here and call it a night.